Hello, everyone. Okay, let's start the lecture. Today, we are going to discuss diffusion models. What are these models? What they do? Why are they better than previous approaches, previous architectures? Okay, let's go. What task do diffusion models solve? As we discussed before, we talked about GANs, wires, image generation, and in fact, diffusion models are state-of-the-art models for image generation. But they're also used in text generation, audio generation, and etc. On the right, you can see the examples of images that diffusion models generated. Now, such architectures like DALL-E 2 or some models of OpenAI and other companies, other big techs, use diffusion models in the core. Okay, so today diffusion models are very popular. As similar to GANs, diffusion models generate images from our distribution given a noise to input. Again, we will discuss Gaussian noise. You could see the idea here. But while GANs need one format to generate image from noise, diffusion models try to generate image during many steps, and the core idea is that during each step, diffusion model denoises the image a little. So you can see here, like we start with pure noise, and in the middle step, you can see some parts of the image, but the image is noised, but not so much as at the beginning. And each step, the noise is smaller and smaller, and finally we obtain the image from our distribution, from our dataset. Okay, so the core techniques here are noising and denoising. Okay, if we have an image, we want to noise it. We want to add noise to it, and it's a very simple step. Again, in fact, we want to a second. Yeah, here is good. We want to take image x0, take noise from Gaussian distribution, and mix them with some scalars and obtain xt, some so image after some step. We will discuss later what coefficients we should take. But now the idea is that adding noise is very simple. Each step, here you can see that if we have xt minus 1, and we want to obtain xt, it's not a deterministic process. This means that xt can be random. So if we will obtain several xt's, they will be different, even if we have the same xt minus 1. So xt is a random variable from Gaussian distribution. From Gaussian distribution with mean xt minus 1, and this beta and square from 1 minus beta, and beta on E variance. So each step after noising, we should sample from Gaussian distribution. On the right, we simply obtain the distribution for all images given x0 from input. We simply multiply all distributions, but it's not very interesting for now. Okay, this calls forward process. When each step we noise the image. Also, we have fast forward process. I don't think that's a name from some literature, but for simplicity, let's call something like this. It's the same as forward process, but in forward process is if we want to obtain xt, we should make t steps. But it is obvious that we can derive some formula to obtain xt directly from x0 without many steps. The derivation says that we should sample from this distribution where alphas are derived from betas. So if we have betas, we can derive alphas and sample from this distribution directly xt without t steps, sample with only one step. So in fact, if we have x0, we can obtain xt with no cost, without these steps. More interesting is backward process. If we have xt, we want to obtain xt minus 1. And this is not obvious. How can we do this? So for this task, we want to train our model. Our model will we'll give xt and t for our model. Xt because our distribution is conditioned on xt, because we have xt and want to obtain xt minus 1. We go from left to right. And t is the number of steps, because on each step there is different noising, and want our model to consider this noising. And our model will return two values, the mean and the variation of the distribution, and the variance of distribution, sorry. It's very similar to Y approach, where our encoder returned mean and variance. Here is the same. So we return, the idea is to return the distribution, because each image, in fact, is not an image. You can see that each node is a distribution. So that's why we want to return the distribution, not a point from it. So P is a distribution on xt minus 1 given xt. And we obtain this distribution using our model that returns the mean of distribution and the sigma of distribution. Theoretically, we can show that if Q is normal distribution as we have taken here, the reverse process should be also normal. Okay, so what we have now? We have a model that takes xt and returns xt minus 1. Xt takes xt and the number of steps, sorry. So how to train the model, because we want from it to work correctly. Okay, let's say that we should have some loss on step t when the model predicts xt minus 1 from xt and t, and call this loss LT. So the final loss will be sum of these losses. Interesting that L0 will be simply probability of image of first image, because we want from our distribution to be simply the image. It's so we don't check the loss on distributions. We check that it will return image. It's L0 for x0. The similar way we assign LT, the final loss, yeah, as scale divergence between two distributions. We discussed in GAN lecture what is scale divergence. If you missed it, I will remind that in fact it is a loss on two distributions. We have two distributions. This loss is small if the distributions are similar. It's not mathematically correct, I think, because what is similar, yeah, but I think the idea is okay. As far as there, it is okay. So the idea is to make two distributions similar. What are these two distributions? T on xt is simply the Gaussian noise, yeah? So, qxt from x0, like we have x0, we obtain xt, yeah, sorry, and this is Gaussian noise. So we want our model pxt to be similar to Gaussian noise. I think it's okay. Okay, and the most interesting part is other LTs. We want to make similar to distributions, Q and P. What are they? We have P xt minus 1 from xt. Okay, we have xt, we obtain xt minus 1, and this is distribution on xt minus 1. But the Q distribution is slightly different because here we have xt on xt minus 1 from right to left, yeah, from t minus 1 to t. But here we have xt and we want to obtain xt minus 1, so it's distribution on xt minus 1. So we swapped two variables. In fact, this is okay. Why? Because we say something like we have a model that wants to predict xt minus 1. But we have a real distribution that we know from xt minus 1 to xt. So having this distribution, let's reverse it, reverse the process, and obtain distribution from if we have xt and obtain distribution on xt minus 1, considered on xt. And in fact, we reverse the arrow and say like these two distributions should be very, very similar, because in fact we want from our distribution to work like this. And what we see, we have Bayes theorem that says that Bayes theorem, in fact, this is equality. Like it helps us to reverse two variables. For example, we want to obtain xt minus 1 considered on xt and x0, yeah, because we have x0 in the beginning. And we reverse xt and xt minus 1. And also we have two additional distributions, but they know them, because from x0 we can obtain both xt minus 1 and xt. Okay. And after some derivations, we obtain the formula that xt minus 1 considered on xt and x0 is equal like this. In fact, it's the sum of two images, but with some coefficient, with some scalars. Okay, I will give more understanding on these formulas without any mathematics. I will try this. Okay, we have some black box Bayes theorem. It helps us to swap variable on which we have distribution and variable on which we consider. For example, in this example, let's see here, we have distribution on xt and consider on xt minus 1. And Bayes theorem helps us to derive it from distribution where we change the places of these two variables. Yeah, this is the idea of Bayes theorem. So we want to make similar. We have the true transitions Q and our model P, and we want and these are these are two chains. And we want from our model to be similar on Q. But the Q goes from right to left and P goes from left to right. So the idea is to reverse the Q process with Bayes theorem, because after Bayes theorem, we'll obtain Q distribution on xt minus 1 considered on xt, where we changed the places, and the arrow will reverse. And these two arrows should be very similar, and then our model will work good. Okay, the other question, why x0 is here? The idea is simple, that when we consider xt on xt minus 1, we in fact can drop x0, because what is the process? From x0 we obtain xt minus 1, and then we obtain xt. And having xt minus 1, we don't need x0, because there is a formula how to obtain xt from xt minus 1. And x0, in fact, can be dropped because we simply can obtain xt from xt minus 1 like this. But when we reverse the process to obtain xt minus 1, x0 is essential. Why? Because we have xt, and now we can't go back to exactly 1 xt minus 1. Why? Because this is a distribution. And if we have xt minus 1, we can sample different xt's. So we don't have bijection here. So several xt's can be sampled from the same xt minus 1. That's why we can't go back. More correctly will be say that from several xt minus 1s, we can sample the same xt. And so we can go correctly back. Because there exists some xt minus 1 to go back, but we don't know which. We don't have to correctly say which one xt minus 1 we had, but we should estimate probabilities of xt minus 1. And to make it more precise, we should use x0, because using x0, we have extra dependencies on which xt minus 1 can be sampled. For example, if we have exact xt and want to estimate the probability of some xt minus 1, and the probability will be very, very big. But using x0, we can say that such xt minus 1 such xt minus 1 has small probability to be generated from x0 during the process queue. And this is extra information will help to make probabilities more precise. Okay, so we use x0. In fact, we can say that this is equals to q from xt minus 1 x0, and use Bayes theorem to reverse these two variables. So from this we will obtain, it's not equality because there are some extra multiplication, but we know all the parts of the formula, so can obtain something like this. And this is the distribution on xt minus 1. And we want this distribution to be similar to our distribution from our model. Okay. So this is what is going here, why we use Bayes theorem. And after using Bayes theorem, we know this one. It's simply what we have here. It's normal distribution. It's normal distribution with betas. We know these parts. It's fast forward process, obtaining xt from x0, xt minus 1 from x0. And we obtain the formula for this. It's not, I believe the idea is, you will understand the idea. So we know the distribution of this, we know the distribution of this. It's simply mu normal distribution mu and sigma, and we should calculate Kyle divergence for these two distributions. These are two normal distributions, so we can easily compute the Kyle divergence. We discussed it in the previous lecture, and don't worry, we will discuss it a little bit later. So this is the loss. It's sum of many additions, many other losses. And next we will discuss training. Next we will discuss loss a little bit more, because from this, it's hard to code. You can hardly code using these formulas. So let's discuss formulas more practical, in more practical view. Okay, how to calculate Kyle divergence? We will say something like our predicted variances will be a constant. Exactly, they will be sigma squared t will be beta t. We will take something like this, and our Kyle divergence will derive into a formula like this, where mu t is mean from our model, and mu t is mean from our Q distribution, from our real distribution. Something like this. I think. You can see it here. So here you can see the fast forward process, as we discussed. In fact, it is the formula for this. Yeah, we discussed in the GAN lecture. In fact, in the via part of GAN and via lecture, the reparameterization trick. When we have Gaussian distribution, we can derive the formula for our random variable. It will depend on a random variable from standard normal distribution with mean 0 and variance 1. So we do the same if we have this mean, yeah, and we add, we take variance, in fact, square of variance, and multiply it on standard noise, normal noise. And we will calculate the mean. In fact, we derive in fact, we derive x0 from xt. So this is like the mean of this. Okay, so Kyle divergence derived to this formula, and we can optimize this loss. You can see here mathematical expectation on Q, but in fact we can use simple. We can take batch, take x0s from it, obtain xt's, and take the mean loss, and this will be approximately the expectation. It's a Monte Carlo approach. But in practice, it's better to work with not with means, but with noise. We can see here that we can derive mu from epsilon. What is this? It is generated noise. And from our model, we want to predict not mu, but to predict noise, because before we tried to predict mean of the previous distribution. And when we said that variance is fixed, it's a constant, we can say that we simply predict the mean of distribution, we predict the previous image. So we avoided complex distributions in loss and so on. And now what we say, let's predict not previous image, but predict noise that our previous image was noised by. So what we did before, when we had xt minus 1, we sampled from this distribution. As I said, we can use reparameterization trick, generate noise from a standard normal distribution, and add noise multiplied on square of variance and add it to mean. And this will be generated sample from here, the same thing. And now let's predict the noise that we generated from standard normal distribution here, epsilon. So we have a real epsilon and we have predicted epsilon. Here, in fact, is xt, like this. And we can derive this formula to this formula. These are exactly the same two formulas, but in a little bit different view. Here for means, here for epsilons. And let's simplify it. Let's drop this coefficient, the scalar, and obtain simple square of difference of noises. And in practice, practice showed that this simple loss works better than this one and the previous. So everyone uses noise prediction. Okay. Let's discuss finally how we train and after how we sample. What is how we train? In 4 cycle, we sample x0 from our distribution. In fact, from our dataset. So the start point is our image, like this image of a man. Then we don't want to optimize all losses at a time. Let's optimize at each step, optimize only one loss. So we sample T, and we will optimize LT. We sample epsilon, as we discussed, the noise, standard noise. And let's optimize LT using this loss. We simply calculate xt. It's in this manner. We'll discuss later how to take alpha t. So we put it to the input of the model, put the number of step t, and obtain the noise. And we want two noises to be similar, so we take square of difference. Yeah, and take the gradient of it and optimize. And repeat. It's a simple schema. In fact, we'll, of course, use batches and so on. Optimizes. Okay, we trained our model. What should we do now? Now, we should go from left to right. Backward process. Generate xt, not x0, xt. It's simply the noise from standard normal distribution. Then go from left to right and try to denoise the image. We should sample the noise and sorry, I think I should draw a little. This is the part of denoising. So this is the mean of the distribution. And after we add, this is, as we said, that our variance should be constant, sigma squared. So, and after we add sigma multiplied on noise from standard normal distribution. In fact, is again the reparameterization trick, and it is the same as sampling from the normal distribution with this mean, yeah, because this is our mean, and square of this variance. Okay, what the formula we have here? In fact, it's not very hard. We have the forward process where we obtain xt from xt to minus 1. We write this using reparameterization trick. And now we derive xt minus Yeah, and here we have now xt is something from xt minus 1 and epsilon. Now our model predicts epsilon, and we can rewrite to obtain formula for xt minus 1. So all things go to left, and xt minus 1 stays in right. And we have the formula for xt minus 1, which depends on xt and epsilon, and the noise. But here is the noise. We predicted it with our model. And here is xt, because we go from left to right, and we have xt and obtain xt minus 1. And again, as I said, we obtain the mean of the distribution. And after, we should sample from this distribution by adding sigma t multiplied on standard normal noise. And because of using this random approach, when we don't have deterministic chain, we sample from distributions. This will help us to obtain different images at the end and obtain more diverse samples. For example, in GANs, we had, as you remember, problems with diversity. And here we make many steps with sampling on different levels, and this also helps to generate more diverse data sets. Okay, but the right explanation why we sample diverse images is needs more maths, probabilistic theory, and so on. So it's about idea, not the right explanation. Okay, as I said, we have a problem how to sample, where we should find alphas, where we should find betas. So as you can see, alphas are derived from betas directly. So let's discuss how to take betas. In fact, what are betas? Betas control the degree of noising. How much noise do we add? As you can see, the bigger bet is better, the more noise we add. So that's why what we want from betas. The bigger is t, the smaller noise we add, because the bigger is t, so the smaller is t, the more noise we add, because on 0 step, we should add 0 noise. On t step, we should add as much noise as we can. Yeah, here you can see the graphics, but here is alpha, not beta. What is alpha? Underline. It's the formula to obtain xt from x0. Yeah. And here we can see that there is 1 minus alpha. So here the smaller alpha underline is, the bigger noise we add. So that's why the graphics decrease here. But for betas, it will be increased. Okay. So here are some approaches how to choose scheduling. This name scheduling. First is linear scheduling. We take first beta, last beta, and make line between them. Yeah, obtaining the sequence of betas. Another approach is cosine scheduling. You can see the formula here, which is derived from cosinus. And what is the difference? We can see here that the graphics of linear decrease faster than cosine. And you can see on the images, what are these images? These images are images from different steps. This is the 0 step, and last is the last step. And we can see that that's for linear, the noising is faster than for Cassine. Because, as I said, linear decreases faster. So fast and noisy. And when you choose scheduling, you can take in mind what you want. For example, when in some papers for text diffusion, not for image diffusion, the authors say that it is essential to noise faster than for images, because text domain is discrete. So in fact, we can pure work with it. So first we vectorize the tokens as for every other approach. Yeah, and then work with vectors. But in space, for each token is a point. Yeah, and the problem is that it is a discrete space, because if you take some point near to token point, the model can easily say that, oh, I think they're close enough and they're the same. That's why if you add small noise, it would be the model can easily say what was here, because for images, for example, I think for this image, we still can say what is this, or for this. Yeah, but for this, it is hardly, you can hardly say what was in this image. And for text domain, even if you add much noise, because the points in the space are discrete. For example, add a noise. After adding noise, you will obtain some distributions around these points. And because this is discrete, the distributions don't intersect. And you can easily, for example, after adding noise, you will result for example, for these 4 tokens, these orange 4 tokens. And it is easy to say from what real token each orange token was obtained, because the space is discrete. That's why it is essential to choose faster schedulings, faster than even than linear, and this will help diffusion to train correctly. Sorry, it could be a little bit unclear, but the idea is that choosing scheduling is also very important. But for images, you can take linear schedulings, Cassine-set schedulings, or for example, search for some other schedulings you want. Google or ask ChatGPT, or it's some extra materials, and maybe the result will be better. Okay, and here this is the end of our lecture about GANs. That we have 3 properties we want from our generative model. Fast sampling, to sample fast, high quality samples, and we want images to be beautiful, they should have quite high quality, and mode coverage or diversity. We want our model not to generate the same image, for example, or similar images, but to generate diverse images from whole data set. And the problems of GANs and FIAS that they both had fast sampling, but GANs had high quality samples, but it had mode coverage. It had mode collapse problem when model generates from the same mode, so it generates similar images. And Vias generated diverse images, but the quality wasn't good enough. The well-known problem that Vias generate blurred images for some tasks, for more difficult tasks. But diffusion models can generate high quality samples. Intuitively, it generates for many steps. So each steps it's a little bit it denoises a little bit and improve the quality a little bit. And it generates diverse images because, as I said, we have many samplings from many distributions. And even if you start with the same noise, it will generate another image, different image. Again, it's more about ideas, not fully correct mathematically. But the problem with diffusion models that sampling is very, very slow. Why so? Because we have many steps. In practice, diffusion model generate images for 1,000 steps, 1,000. And you can imagine that number of steps is really, really big. Don't worry, it's not take hours, but it takes much more than GANs or bias or other generative models. There are some works that distilled the diffusion model to diffusion models with less steps. As I remember, there was a work that proposes a model that generates images with very good quality for 4 steps. But we will not cover this topic today. So the now diffusion models is a really state-of-the-art approach, generates high quality samples. This architecture is used in many novel products like ChatGPT, Anthropic, DALE, and so on. And I think this architecture has a future in image generation, and I believe in other domains too. Another part of our lecture will be the discussion of stable diffusion. We discussed the simple pipeline of diffusion, but of course, to generate high quality images using but of course, there were some works that extended this approach. For example, how to generate images using the text prompt or another image. For example, in this pipeline, stable diffusion, we can see that we want to generate parrot sheep using this image. And stable diffusion generates parrot sheep in this and the background is very similar to this image. Let's discuss how we can obtain text prompt in the input and image in the output. Another image in the input will work very similar, so we'll drop this part. So in our pipeline now, we have text prompt in the input and generated image in the output. Okay, first we give the text input to text encoder that returns us some vector embeddings. And now, again, we have a diffusion steps, and we generate random noise from normal distribution, standard normal distribution, and generate the output. But the first problem is, I think the main problem is how to consider the text tokens where we generate the output. First, let's discuss first idea. The problem of diffusion also is that it takes very much time to generate. And moreover, on each step, we have a big image. And first works worked with small images, but in fact, to use this model in reality, we want to generate high quality images like 1,000 to 1,000 and more, 4,000, 4,000. And if we will use such big images, the generation will take really long time. And moreover, it will take much resources. And if we'll compress the images to smaller, we will lose quality, yeah, with some details and so on. So the idea is to compress images into latent vectors. Again, uh, 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 the idea is to, like, for example, when we talked about variational autoencoder, we said that we have encoder part and decoder, and in the middle we have latent representation of the image. Is the same thing. We have encoder and decoder for images. Encoder encodes image to latent representation. Decoder decodes image to from latent representation. We shouldn't use exactly variational autoencoder. We can use any other autoencoder. Or, I mean, we can use architectures for encoder and decoder and use them in the pipeline and train together. So here is the visualization. We have image decoder. It takes image, maybe a noised image, maybe a pure image, and decodes it into some tensors. In fact, in this pipeline, we start with this. We generate latent vector from from a random image. We generate random image. We decode it to latent vector, that is like random latent vector, and start the diffusion process for it. And now the size of tensor is much less than the size of the input image. And the idea here is, yes, we compress the information, but because we use decoder, we extract useful information, local information, global information. And if we used simple compressing, like resize, yeah, it will lose much. It will lose important information and will leave some unimportant information. And decoder, when we train encoded decoder architecture, the main idea is to learn how to extract useful global and local information and put it inside a latent vector. So inside, for example, this latent vector, we have really useful information. And after we will decode this latent into the image. Okay, so as I said, this is encoded decoder architecture. We have an image, encode it into latent vector, and then decode back. And during training, we take original image from our dataset, we encode it into image latent, and we can run a diffusion process. And during generation, we start from random latent vector, then we denoise the latent vector, and finally we have a processed image information and decode it into generated image. So we need both encoder and decoder. Also, we had a problem that we can't consider text token embeddings when we generate the image. So our model, we have some, you can see here the diffusion process, many steps, and one step, for example, we take our model, some transformer, some unit architecture with attention blocks. And the idea is to use text embeddings in our transformer. In fact, we consider our attention mechanism on these text embeddings. And each step, our model also takes not only xt and t, but xt, the current image, t, the current step, and text embedded, and outputs the xt -1 again, but considered on text embeddings. And this helps us to generate images considered on the text prompt. Talking about text encoder, we will take clip encoder. As you remember, we also discussed clip, the model that has two encoders for images and for text, and tries to if pairs of text prompt describes the image, it encodes image and text prompt and tries to put close embeddings of this image and this text prompt. So this is a model with property that similar text prompt and image, their representations are close enough. And we use text encoder, and this also helps us to generate images considered on the text pattern. So these are the core ideas of Stable Diffusion. Of course, there are really many details: how to train, how to use some, I don't know, how to some ablation studies, some mathematics. But in fact, this is a core description how to train your diffusion model on your tasks, the most simple approach, and some, I don't know, can't say it is a very difficult approach, but a modern approach, how to make your diffusion works really good and generate high quality images, not only toy images like 64 and 64, or yeah, something like this. Of course, you can always check sources for more information if you want. Yeah, I think that's all. Thank you for your attention. If you have any questions, you can always write them in our Discord. We'll try to answer them. Thank you.